Okay, so we've driven it about 50 miles. The EVAP light or codes have not come back. I'm not sure if those tests have been completed. I did not look at that information yet. And I have cleared the codes a couple of times since because the VVT system did set codes, the P0014 and the P0017. One is a cam actuator performance or cam sensor performance code. The other one is a correlation code between cam and crank. And whenever it sets the 117 code, it stops giving me accurate data on the scan tool. So I did record some data. We didn't have the camera with us, but I went ahead and screen recorded on the Snap-on Zeus. And while we were driving, I came to a stop sign and it started running rough. And I looked down at the data and it showed that the variance was 0, which I knew was inaccurate, and it never changed from that point until we cleared codes. So I just had Valerie clear codes while I was driving, and then we started getting data again. So sometimes the cam actuator is actually sticking in the retard position. And then sometimes it's sticking in the neutral position. So it's sticking, both ways depending on where it got to when it stuck. And I think what's happening is I think the solenoid itself is just sticking once it gets hot. It's a little warmer today. It's about 40 degrees outside today. We drove it around for about a half an hour before it acted up. So hopefully it's still warm enough now that we can do some checks. We can check resistance of the solenoid. I don't think it's going to be an electrical issue of that solenoid, because if it's an electrical issue, it shouldn't stick in the retard position. It would basically, the spool valve inside that actuator would go to 0, and it would cause that timing gear to go back to the neutral position or back to the advanced position and lock. I don't think it's an oil pressure issue because the oil pressure gauge was above 40 PSI the entire time we were driving. Although when it first started to act up, it would only act up at the lower RPM area. It wouldn't move until about 1500 RPM, then it would start moving. The further we drove it, the worse it got. That is often a sign or symptom of low oil pressure. If the system won't operate properly around idle or around 1000 RPM, it's because the oil pressure is too low. That's really common on the Ford 3-valve Tritons. A few other vehicles, I have a video on a Kia that was stalling when I'd come to a stop sign because it didn't have enough oil pressure once it came down to an idle. But this one, the further I drove it, it would do it even at 3000 RPM with 50 or 60 pounds of oil pressure. I'm not sure if oil pressure was recorded at the same time when we were driving. It might be in my PID list, I'm not sure. I'll just have to double check that. So we'll go over that. Let's jump back inside. We'll look at that recording, look at that data, and see what I was looking at. So here I'm using ShopStream Connect on my computer, just reviewing the data recorded with the Zeus. You can do this with any Snap-on scanner. When you hit that save button while watching data, it saves a scanner movie, and you can review it later on using a laptop or computer. Software is free on Snap-on's website. So it looks like this. All these on the left are the data PIDs I recorded. All the ones that are highlighted in green is what's visible on the screen. If I scroll down, we can see that bar graph move, but you can see the active value on the left-hand side of the screen. That value is anywhere where this green cursor is. So let's go ahead and zoom in a little bit here at the beginning of our test drive. On the bottom left, I have the engine runtime as we're driving the vehicle, map sensor, vehicle speed, engine speed, and our exhaust cam data. So here at the beginning, when I started the recording, I just wanted to get some base information at idle. I'm at 5,300 feet, so over here on the right is our map sensor, bottom right. Current value is 9.4. Now that's not how much vacuum I have. We have to look at our maximum, which is our barometric pressure, and this was during a wide open or heavier load situation. But I know that that's accurate for my current elevation at 5,300 feet. So we take this 24.5 minus this 9.4 and we get 15 inches of vacuum. That's pretty normal for me. We see 14 to 17 inches of vacuum on most vehicles. So keep that in mind. If you're at sea level, you may see a slightly different reading there. So sitting here at idle, we have no cam angle. Our actual cam angle is at 0, desired is at 0, variance is at 0, and no duty cycle on our solenoid. As we begin to start driving, we see this little blip, and I'm not sure, I may have just snapped the throttle here to make sure that I was recording data, because it's just, there's no vehicle speed, it's just a throttle blip. Let's jump forward until to where we start driving down the road. And I kind of want to zoom in on where we first start commanding the exhaust to move. So our engine RPM just broke over 1,000 RPM. We're at 4 miles an hour, and the PCM decides it's time to start giving ourselves some cam retard. Increase that valve overlap, increase our power a little bit. So we can see the command, the duty cycle going to that solenoid, begin to increase. Let's just jump right up here to where we see that level out. That's 80% duty cycle on that solenoid. Desired exhaust cam degree is 12. But if we look at our actual is just sitting here at 0 doing nothing. Looking over here at the left, our coolant, we're fully warmed up. We're 197 degrees Fahrenheit. So we see the variance start to go up because this is sitting at 0. Our actual is at 0 and our command is rising. So because the command is rising and it's not seeing a change, that's where our variance starts to go up. So if you're trying to find the faults, it's best just to look at the variance, and then you can look at the details after that. So looking at the solenoid, it's commanding it. It's not seeing anything happening. So the command drops, it rises it back up, it drops, it rises it back up. Basically, the PCM is saying, hey, I think our solenoid is acting up. It might be stuck. Let's give it some juice, let off, give it some juice, let off. Then it just kind of holds power to it. When we see this variance drop, it's dropping because our cam timing is actually going up. So if we look right here, our cam timing went up, and it's now matching our desired or really close. So at this point, the PCM's like, okay, we can drop our duty cycle here because we just need to maintain position. Let me zoom out. And, we're just continuing our test drive. Looks like we went on the highway for a period of time, 40 miles an hour. And if we look over here on the left, we see some, ups and downs with our variance. Now, on a good running vehicle, the only time you'll see variances is a few degrees on rapid throttle changes, because it does take a little bit of time for that cam to catch up with what the computer's wanting it to do. But when we're just maintaining, a load and there's not that much fluctuation, we shouldn't see this much variance. It shouldn't be that noisy. So let me continue on where I mentioned earlier on that we had a glitch. We're driving along. Let me find my speed. You can see our vehicle speed here on the bottom right. We're going along on the highway and we come down to a stop. So we can see that I stopped at the stop sign for a short period of time, and that was to look at the data and then hit the save button. If we look up here at our variance, on that deceleration event, because I probably let off the throttle around here and we start coasting down, we start seeing that variance rise up. So I'm going to zoom into that section. So the variance starts to rise, and the variance reaches this point here of 25 degrees. So the cam is at 25 degrees. The command is 0. We have no duty cycle on that solenoid, and yet the cam is stuck at 25 degrees. So we go along, and then for some reason it shows that the cam drops to 0. I don't know if this actually drops to 0 or if the computer just stopped reporting for a little bit. And then we see this spike jumping up and down. That's because the computer isn't really trusting the data, or because we're having a pressure issue with that solenoid. It's not able to control the oil flow to that cam. Or we can also even see this on vehicles when we have low oil pressure. There's not enough oil pressure there to control it, so that cam just starts bouncing around. If we look down at our duty cycle, we get a big spike here. It jumps up to 100% duty cycle. So it's attempting to unstick that solenoid. It says, hey, we have an issue. We just need to slam this thing the other way and then let go and see what happens. It's still detecting a fault. That's when we start jumping up and down here. We scroll to the right just a little bit. And if we go right over here, basically just nothing happens. It finally goes down to 0 and stays at 0. But are we actually at 0? Let's look at our engine speed. Our engine speed is 600 RPM, so we're sitting at idle. Now, if we remember back to the beginning of this test drive, sitting at idle, I had 15 inches of vacuum. So our engine's at low RPM, we're just coasting still. You can see our speed is dropping. So let's go past where our speed is dropping, so we know that we're just sitting at a stop at idle. RPM is 540. Take a look at our vacuum. It says our current manifold pressure is 20 inches of vacuum. But that's not our manifold gauge pressure, because our barometer is 24.5. So 20.6 minus 24, or 24.5 minus 20.6. We're sitting at just 4 inches of vacuum in the manifold. So basically we have a race cam at this point, and our vehicle does not want to idle at all. And as we come along here where it stabilizes, we're sitting at 3 inches of vacuum. So not a very stable idle, and this is a good indication that our cam is actually still in the retard position. The computer doesn't know what to do, so it quits giving us data. And at this point I switched over and checked codes, and it set the P0014 and P0017 codes. So once it set those codes, it stopped reporting data, and it stopped trying to command the exhaust VVT. In order for me to get this data back, I had to clear codes. So now you guys see what I was looking at. Let's go ahead and go under the hood, and let's check the signal going to that solenoid. Honestly, I don't even think it's necessary at this point. I should just call a bad solenoid and replace it and not worry about it. For the sake of those that want to test everything and make sure that it's good, I'm going to use the lab scope for this. We could check resistance, and you could do that with the basic multimeter of the solenoid to make sure that the windings are still good. But everything beyond that, we're probably going to need a lab scope to verify. We could take, just some jumper wires, power and ground, jumper the solenoid, and see if we get movement on the scanner data. But at the same time, if it doesn't see that command, then it may just set a fault code, and then the data is no longer relevant. We could scope cam and crank sensor and check it when it's in a good position, and then check it when it's stuck in a position we don't want it in. But at the same time, we can normally see that in scan data for a short period of time before it sets the code. So I don't think that's necessary as well. So if I was just in the shop in a customer vehicle, I would just check resistance of the solenoid, make sure that it wasn't open. But because it's sticking retarded at times, I know that it's not an electrical issue. I probably would have just called a bad solenoid by this point. Right here is my camshaft position sensor. This is the exhaust side of the engine. It only has a sensor on the exhaust cam. There is no variable valve timing on the intake cam. Right back here by the power steering pump is a connector for the variable valve timing solenoid. Now, in order to remove this solenoid, we do have to move the power steering pump. The solenoid won't slide out far enough out of the head to clear this. Some people have different methods of doing it. We'll get to that when the time comes. There's just 2 wires going to this solenoid. I did not pull, the wiring diagram to see which one is which. What I'll do is I'll just grab the scope. We'll connect one lead to ground, and we will, just back probe the solenoid. We'll probably have a constant power and a switching ground, which will be pretty easy to verify. A couple more things we can do with the Zeus. Because it's a Windows-based platform, it has a few more options than the other Snap-on scanners have. It doesn't really matter which one you use. This one, I just have a little more flexibility. But we're going to go back to the guided component test, and hopefully that'll show us where our connections should be. So we're gonna go to Engine. We're going to go to Camshaft Phaser. Make sure there's nothing else here for that system. I see cam sensor, crank sensor, and the phaser. We're worried about the phaser, so that's what we're gonna look at. It gives us information for resistance, so we can check that later. It's connected right now, so I think we'll just leave it connected and do the duty cycle test. So it tells us our solenoid control is actually gonna be on the high side. We're gonna have a 12 volt control, and we're gonna have a low reference, which is gonna be ground. It doesn't give me, it doesn't give us colors there. Low is gonna be black or white and black. And then the gray or the brown is going to be our control wire. So I do see the brown wire. I'm just going to back probe this. I probably should have grabbed a slightly smaller back probe, but I think we got a good connection there. I'll start up the vehicle. Okay, so right now we don't have anything on the screen, and we're checking for duty cycle, so we won't even see if it has 12 volts. But with the Zeus, there's a button here at the top called meter. We can hit that button, makes the meter go full screen. We'll hit it again, and it gives us that meter in a pop-out screen. Now I can minimize that. I can go back to this other screen, and I'm gonna go back to the home page and click on scanner. That's going to allow me to go back into functional test and actually command that actuator on and off. So there's CMP actuator test. The solenoid test is just an on-off test. If we go to actuator, it should let us perform a duty cycle. So I went 5 degrees, and that looks like it's about a 50% duty cycle. 10 degrees, I didn't see much change in the duty cycle on the screen. But I think what's happening is, once it gets to a certain angle, then it just has to maintain that 50% duty cycle to hold that camshaft locked in that position. And right now, we can hear that it's kind of running rough. That's because it got stuck in that 50% position, and my cam is probably too far advanced. So let's just jump into engine data real quick. More than likely I set a code because it's showing me 0 variance. Let's go back. Code menu, display codes. Yeah, so I set both of those codes again during that test. So I'm going to clear the codes. I'm going to leave it running, because sometimes that camshaft actuator will relock once you shut it off. Let's go back to data. Let's look at this before it sets the codes again. Yeah, it's just not happy with the position of the camshaft, so it's not even going to give us a degree. But we know that we have a signal from the camshaft because we have camshaft position sensor RPM. And the way it's loping, it's jumping from 500 to 700 RPM. So we have a signal from the camshaft position sensor. It's just, it doesn't like the position that it's at. I'll go ahead and shut it off and start it back up, and it'll probably go into a better position. Okay, so we're back to running normal. Our cam angle is at 0. So everything's still at 0, but now it's running fine. It took a little bit of cranking to get it to fire up. You can smell the fuel is starting to flood out a little bit. I'm gonna go back in here, go back to our functional test. Okay, so we're not exceeding 14 volts. There is no feedback or kickback on this one. You know, it looks like a regular duty cycle, but I think we're going to be fine with everything there. I think that solenoid is just sticking. And right now it looks like we're about a 50% duty cycle. When I kick this up, the duty cycle will change for just a short period of time to get that cam to move where they want it to move. And then it goes back to that 50% duty cycle to hold it in place. We exceeded our time, so let's go ahead and jump back out of here and just check the resistance of the solenoid. But you know, we can already tell that the solenoid is sticking, sometimes closed and sometimes at the 50% mark, which is locking that camshaft in whatever advanced or retard mode we have it. And for this test on the scan tool, it's going to have us connect our scope leads together. So we're not going to use the ground anymore. We're going to be connecting the scope leads just so we can zero out the values on the machine. So those are connected now. I don't have any other grounds connected. I'm going to actually have to move these leads to channel 3 and 4. Do we wish to calibrate? Yes, we're going to calibrate. Connect channel 3 and 4 together. Calibrating all scales. It says right here in the information, resistance should be 8 to 13 ohms. So right now we're at 0 ohms because I still have these connected. I did not bring my AES wave kit home, so we're just going to use 2 back probes. Lift up the safety lock, push the release button and unplug it. And I'll attempt to get both of these in there while watching the lab scope screen. So it's in auto scaling right now, that's why it shows mega ohms. We could go to manual range because we know that it's supposed to be 8 to 13 ohms. You can see it changing around, jumping around, and it finally settled out just below 10 ohms. So we are at 9.79 ohms. The spec was 8 to 13. So this actuator resistance value is within spec. And it jumping around is just me wiggling my fingers here. So electrically testing it, it's good. We have a good command. On our signature test, we saw 0 to 14 volts. That means that our power side of that solenoid is good. We don't need to double check that. We can see power coming through the solenoid. The solenoid's not shorted, we checked that. Basically, the solenoid is sticky internally. We could try cleaning it. We could try running the BG flush there, which I'm gonna do anyways on this engine just to clean out the rest of the system, but I don't think that's gonna fix our issue. More than likely there's some scoring on the actuator. A lot of times the screens that are supposed to prevent particulate filter from entering that solenoid, those screens will tear out and then particulate can get in there and gum it up, or the screen itself goes in there and it scratches that surface. Once the system gets hot, everything kind of expands a little bit, their tolerances get smaller, and then it starts to lock up in places. So that's more than likely what's going on. I'll get a solenoid. I don't know if I'll go with an aftermarket one or a factory on this unit. The aftermarket ones are about 30 bucks. The factory one's about 80 bucks. Because we have to pull the power steering pump off and everything else, we're probably better with the factory unit. But Rock Auto has the factory unit for about half the price of my dealer. So I may go with Rock Auto, which means it'll take me a week to get the parts. But once I get the parts, I'll show you guys how to throw that in. We'll double check it afterwards and go from there. So I finally got some parts. I have a factory GM VVT solenoid. I'm gonna go ahead and install that right now. The last couple of days I've been driving it just to prevent the vehicle running rough. I just unplugged the solenoid. If you unplug it, the engine light's gonna come on, but it won't ever activate that system, and that'll prevent it from sticking in an activated state and cause the engine to run rough when you come to a stop sign. The engine light's gonna be on no matter what, so I may as well have it running the way I want it to run. So on this connector, we have this gray tab. That has to be lifted up like it is right there. You can see the little gap at the top. And then we can push on this black button to release the tab in there. And then it'll unplug off this solenoid. Now, like I mentioned before, this solenoid, I'm pretty sure it's gonna hit the power steering pump. It's been a while, but if I remember right, we have to unbolt the power steering pump. We don't have to take it off. We just need to unbolt the bolts from it, which to do that, we need to take the belt off. So we'll go ahead and start there. We'll take the belt off, unbolt the power steering pump, kind of move it out of the way, and then we'll unbolt this VVT solenoid, take it out, and we'll take a look at it and see how bad it looks. Okay, so now we can remove the solenoid. The solenoid has one 10mm bolt, or 10mm headed bolt right there. Once we pull that out, we can give this a little wiggle, break it free, and it'll slide out. There's an O-ring at the back end here, so we just have to get that to break loose before we can slide it out, because we don't want to, try to force this out and have a piece of it break off in the head. So the screens are intact, at least 3 of them. I'm not sure if there's supposed to be a screen down here. I think this is just the oil return that dumps back into the block. I don't think it's the supply. I think the supply is in the middle, and then it can push it through one of these other screens to the valve, but I don't know that for sure. I didn't look up all the operational details. There is some oily varnish on this, that substance there. That's pretty common. I don't see excessive sludge on there. There is just a little bit of debris on the screens. So the new solenoid from GM came in a bag with oil in it a little bit. So the O-ring's already wet. I don't have to pre-lube the O-ring. This one does have an updated design on these screens. They have a little metal wire around them. And this section is open, so I don't have to really worry about anything. I'm just gonna install this. Once we get to that O-ring, we'll have to give it a little bit of a wiggle to get it to seat. Push that power steering pump out of my way. Okay, it's fully seated. Now we'll install the bolt. We can plug in the connector. Latch the safety latch. And now we can reinstall the power steering pump. Okay, so I cleared the codes, everything looks like it's working. I'll go drive the vehicle, make sure that it doesn't set a code. It's probably a little too cold outside right now, so maybe tomorrow when it warms up, we'll take it for a nice long drive, 20, 30 miles. Make sure that it activates properly. I may get some data from that. I probably won't drive that long with the scanner hooked up, but I don't think we'll have any issues now that we replace that, but I'm still going to change the oil and possibly do an engine oil flush. Anyways, if you have this type of issue and you haven't changed your oil in a while, you're gonna wanna change it. If you aren't familiar with doing engine oil flushes, you can make an engine worse by doing it if it's a really bad engine. So you have to be kind of careful. This one didn't look like it had too much sludge in it, but I'm still going to run the BG EPR, the engine performance restorer, in there before I drain the oil. I'll put a new premium filter on, new oil, and then I'll put the BG MOA, which is an oil additive. So that's going to wrap it up for this one. Thanks for watching, and I'll see you next time.